Hello everyone and welcome back to Lesson 2 of AP Calculus AB/Calculus 1. Today we're going to be covering Lesson 2, Limits at Infinity, Continuity, and the Difference Quotient. This is going to be probably the most exciting chapter in all of the calc lessons we have today because it's going to be the first glimpse at derivatives. And the reason why derivatives are exciting is because that's like probably over half of Calc AB is just derivatives. And we're going to see it at the very end of the class what a derivative is. But first, we've got limits again. Oh boy, exciting. But we're going to be looking at some problems we have not seen on limits from last week, specifically when we're talking about limits at infinity. And that's what we're going to be talking about right now. So for limits at infinity, they describe the end behavior of a graph. But what does that mean? It means that basically if I have the graph all the way to the left, like, I only have on the graph here -4. That's like as far as I go. Maybe -5, but it's already off the graph. But what I'm saying is if you were to extend this graph to like negative infinity eventually, well, your graph is approaching positive infinity from the left. It's also approaching positive infinity from the right. In other words, what we're talking about here is that the fact that if I were to ask for, let's say, the limit as x approaches infinity, you're going to get infinity, which of course you would write infinity semicolon does not exist. But honestly, you should write whatever your teacher tells you to write. This is what my high school teacher told me to write back however many years ago. So the most important thing that you can realize for limits at infinity is this example on the right. This example on the right, it's the function y equals e to the x minus 1. I say it down here. But what you realize is that, hey, there's a horizontal asymptote because that's what the horizontal dotted line means. It's a horizontal asymptote, which I'm going to be calling HA for the rest of the time because that takes too long to write. And we're going to be dealing a lot with horizontal asymptotes because a limit at infinity, as you get closer and closer to negative infinity in the x, you're getting closer and closer to -1. In other words, if I ask you for the limit as x approaches negative infinity, I'm going to get -1. I don't even bother doing the positive infinity side because this side blows up to positive infinity. It's not going to work very well, will it? So for the left side, yes, we're approaching -1. And another thing I want you to think about is how many graphs are there out there that actually approach a finite number? And let me be more specific. You don't have to write this down, you can just observe. Basically what I'm saying is there's a lot of graphs out there in the world. Like for instance, there's this graph, which is the graph of y equals x cubed, roughly. Y equals x cubed. Again, you don't need to write this down, you can just watch. But look at what's going on here. This side's approaching negative infinity, this side's approaching positive infinity. If I were to ask a limit, of course, you would write dne, does not exist. But all of these graphs that I can think of, like for instance, here's the square root of x. Y equals the square root of x. And you may be thinking, well, this one surely does not go up to positive infinity. But the problem is it does. And the reason why is because what's the square root of like a trillion? You know what I mean? Like no matter how many zeros you put at the end of it, the number's still getting bigger. Eventually you're going to approach positive infinity. And so that's a problem. Well, not a problem exactly, but that's an interesting observation in the very least. And what I want you to realize is that, hey, the only graphs that really are going to approach a number at infinity, well, there's two answers you can say. The first answer you can say is like, for instance, here's the function y equals 1 over x. And it's actually the next example we're going to look at. So again, you don't have to write this down. But here's the function y equals 1 over x. If I look at it from infinity, you're approaching a horizontal asymptote from both sides. And that's important because that means the limit is eventually going to be 0. But we'll talk about why exactly in a minute. I'm just introducing the concept right now. And then the last thing I want to say before we continue is that there's another function out there that doesn't go towards infinity. And that, of course, is the sine and cosine functions, which look like this. Now, the problem with the sine and cosine functions is that, yes, this goes on forever. Goes on forever both ways. But if I were to ask you the limit as x goes to infinity, in other words, the sine of infinity, well, good luck solving that because you're not going to get anything. Let me explain. If you're constantly oscillating between -1 and +1, then all that means is that it's going to be not settling on a single number. I repeat, not settling on a single number. Long story short, the answer is dne again because you cannot have an answer that's going up and down forever. So we're not even talking about this today. We're only going to be talking about horizontal asymptotes. But this is just something to think about for when you actually take calculus in the fall. So anyways, back here, what we're talking about today, horizontal asymptotes. Here's what I'm going to say. If you want to solve horizontal asymptotes, again, I'm abbreviating it like this. You need to look at the degree of numerator and denominator. In other words, we need to be talking about functions that are basically fractions. And so for that reason, that's the kind of functions we're going to be looking at today. As a matter of fact, here's the first example. I already said it. It's 1 over x. You may also say, Dan, isn't there also a vertical asymptote? And I would say yes. If you want to find a vertical asymptote, then what you got to do is you have to set the denominator equal to 0. Equal to 0. Now technically, yes, you can find vertical asymptotes. I'm not going to focus on vertical asymptotes in today's lesson because it's not a limit. So, and you probably already know vertical asymptotes because those are the easy ones. That's where you set the denominator equal to 0. But what about the horizontal asymptotes? Basically, there's 3 rules you need to know, and let's talk about them right now. So ignore all the words I have right here because the words are just confusing. Let's write this instead. This is basically saying scenario 1, if the degree of denominator is higher, if that happens, horizontal asymptote at y equals 0, you would also say the limit as x approaches infinity of the function equals 0. So these 2 things are true whenever the degree of the denominator is higher. Look at the example I have right here, x plus 1 over 3x squared. In the numerator, the degree is 1. In the denominator, the degree is 2. Since the degree is higher in the denominator, depending on what the question's asking, because I can ask you 2 questions, you got to be careful. If I'm asking you what's the horizontal asymptote, the answer is y equals 0. And if the question's asking about the limit, then the answer is, well, really just the 0. The f of x part is part of the limit, technically. Now, I'm not going to crack down on semantics and notation super harshly, especially during the summer. But basically what I'm saying is just be careful if I'm asking for a horizontal asymptote or a limit. Now, another thing I do want to mention is that there's 2 limits you can have, right? You can have the limit as x approaches positive infinity of your function, and you can have the limit as x approaches negative infinity of your function. The good news is these are always the same. And I have to put an asterisk here because except for piecewise functions. And we're going to be looking at piecewise functions today, so don't worry about that. But they are basically always the same. Positive infinity will always be negative infinity. And I'll even prove it. But that's it for the first one. That's the case where, again, the degree in the denominator is higher. The next case, case 2, this is where the degrees are equal. Degrees are equal. If this is ever the case, you want to look at the leading coefficients. What do I mean by leading coefficients? Well, here's the graph of negative 4x cubed minus 3 over 2x cubed plus 1. As you can see, the degrees are equal. They're both 3. But because of that, I only want to look at the leading degree. I'm going to circle it for us. Negative 4x cubed over 2x cubed. I can ignore everything else. So that means the answer is going to be negative 4x cubed over 2x cubed. Think of it like this. The x cubes basically cancel out, and the answer is negative 4 over 2, which just simplifies to negative 2. And there's your answer for both the limit and the horizontal asymptote. It's the same answer, basically. Now, the only time the horizontal asymptote and the limit will not be the same answer is for the third scenario. The third scenario is where the degree of numerator is higher. If this ever happens, you need to say 2 things, depending on the question. Number 1, you need to say that there's no horizontal asymptote. That's if it's asking for horizontal asymptotes. However, you can never write there's no limit. That doesn't make sense. Instead, if it's the limit, you'd write limit as x approaches infinity. You would say f of x dne does not exist. So what I'm saying here is there's two different answers. Now you may be wondering, should I write equals DNE? And the answer is no, because technically you can't equal DNE. You would just write this, just like this. That's just a little dot there. Let me erase it. That's not a period or anything. Okay, any questions on this first page? Okay then, next. And we're going to be doing more examples later, but next topic, continuity. Continuity basically, it's the same thing as continuous. It means that you can draw the function without lifting your pencil. So just look at this function, it's the sine of x, as you can see. I can draw the sine of x, the whole thing, which again goes on for infinity, without lifting my pencil. Or at least, you know, obviously I'll lift it eventually, I'll have to stop. But theoretically, you can draw it without lifting your pencil. The wording we would use here is you would say it's continuous everywhere. Because it is continuous everywhere. If you want, you can also write interval notation. You can write negative infinity to positive infinity. That's correct as well. And now for the right one, as you can see, there's some not so good business going on here. Because there's a hole in the graph that like jumps from here to here at 0. So what would I say for this piecewise function? Well, basically I would say continuous everywhere except x equals 0, and that's a perfectly acceptable answer. If you'd like the answer in interval notation, I would write this. It's continuous. Here's negative infinity, here's positive infinity for the x values. The reason why I'm saying that is because the answer is negative infinity, comma 0, open parenthesis, union with closed square bracket, 0, comma infinity. That's a poorly drawn infinity at the end. Let me try that again. That's better. So anyways, you have the union symbol. You may be wondering, why is it open parenthesis on the right, the left, and why is the right one a closed square bracket? And the reason why is because if you look at the graph, hole in the graph means parentheses. You don't include it, in other words. And there we get a square bracket because you do include the point. And of course that's because of the fact that we have a black dot there. Okay, any questions on that one? Okay, now let's talk about the types of continuity you can have, because there's basically two kinds of continuity. I know in the notes I say 3, it's really 2. The third one's just a special case of the second one, blah, blah, blah. But the first kind you have is continuity at a point. This is the annoying one because it's a 3-step process. The first thing you need to do is prove that the value exists. That's what f of c exists means. You just have to prove the value exists. I'll explain this better in the next page. The second thing you need to prove is that the limit exists. The limit exists. And we know a lot about limits now, so we'll get better at that. And then the last thing you need to do is you need to prove that the value is equal to the limit. Now let me explain what each of these 3 things mean. 1, 2, 3. Okay, so for the first thing we're proving, you need to prove that the function exists. In other words, not just the function exists, the point exists. So here's a point on a graph. Would you say it's continuous at that point? No, because it's just a point. In order to be continuous, you need to be like a graph, you know what I mean? So now here's a graph, and as you can see here, there's a point on a line. Is this continuous? Yes, very well it is. However, the reason why we have the third check, the reason why we want to prove the value equals the limit, is because you can have the following scenario. You can have a graph where the limit exists, right? This is the limit exists. Why? Limits ignore holes in the graph. So this limit exists, but what if that's an open circle and my closed circle is down here? Now this is not continuous anymore, right? Because you have a hole in the graph. Holes in the graph will mess you up, by the way. Yes, holes in the graph, limit exists, but the function's not continuous. So that's a very important distinction. So we're going to get pretty good at this. Don't worry, we're going to do a bunch of example problems. But that's the first kind of continuity. It's continuity at a point. Remember, there's 3 steps to that. The second kind of continuity is continuity over an interval. The example I have here is the tangent of x, which if you remember what that graph looks like, or maybe you don't, but I'll tell you anyways. Basically, it's a graph that looks like this with a bunch of vertical asymptotes. As a matter of fact, the vertical asymptotes are at negative 3 pi over 2, negative pi over 2, positive pi over 2, positive 3 pi over 2, and as you can imagine, this goes on forever. So then how would you write the continuity expression? So first of all, you can't technically, but we can get close to it. Like we can write it's continuous, and I can start at negative 3 pi over 2 to negative pi over 2, and then I can do union with that to negative pi over 2 to positive pi over 2, and then I can union that with like all the rest of this. You can do that for a while, but you're never going to finish. And so for that reason, you're probably not going to be asked in any question to find the continuity of specifically tangent x, because again, it goes on forever. But the goal here, the reason I'm showing you this is because with these intervals, continuity over an interval, we need to know how to write interval notation. As you can tell, these are all parentheses. Why? Because the vertical asymptote says you're not touching it from the left side or the right side. And then down here I say the last kind of continuity you can have is continuity everywhere. This basically means if you were to write it as an interval, you would write negative infinity comma positive infinity because it's continuous everywhere. Now, as a matter of fact, most functions in the world that I can think of are continuous everywhere. Let me prove it. Here's the function f of x equals x, just a linear line like that. Sine x we drew earlier, looks like a squiggly line that goes on forever. Absolute value of x is a v. Now, even though it is a v, it's still continuous everywhere. In other words, there's no values I can plug in here that break my calculator, so it's continuous everywhere. Then you've got x squared, which is a parabola that just opens up, and f of x equals 5, which is a horizontal line at 5. In other words, all the functions here, and many, many more, are continuous everywhere. However, I think you can agree with me that the functions that are continuous everywhere are not very interesting, and so for that reason, we're probably not going to be focusing on them. We'll probably be focusing on the first two kinds of examples, right? Yeah, isn't that fun? So now, if you're not continuous, we'd say you're discontinuous, and there's two kinds of discontinuities there are out there that break your function. The first kind is a removable discontinuity. This is most commonly a hole in the graph. That's the most common example. It very well may be the only example. But the reason why it's removable, here's what you need to know. If it's a removable discontinuity, how do you spell removable? I guess there's no E. Okay, well, we'll get better at that. If it's a removable discontinuity, then all that means is the limit exists. With removable continuities, the limit exists. In other words, if you were to just remove that single point, like the hole in the graph, then yes, the limit will exist. And then for non-removable, obviously this is going to be where the limit does not exist. Limit does not exist. Here's some examples of non-removable discontinuities. You've got the jump discontinuity, which literally looks like you're leapfrogging from one section to another. You've got the infinite discontinuity, which is also known as a vertical asymptote. That's an infinite discontinuity. And then the oscillating discontinuity. This is actually a cool example. You may be wondering, what function is it? The answer is, this is the function of sine of 1 over x. Let me explain what's so cool about sine of 1 over x. I'll show you on a separate sheet of paper. So think about what's going on of the sine of 1 over x, specifically at x equals 0. Or maybe not at x equals 0, but as you're approaching x equals 0. In other words, when I plug in, for instance, I'll make a table of values. Let's say I have x and y, and I'm going to, for my first point, do 0.1, then I'll do 0.01, then I'll 0.001, etc. So first of all, the sine of 0.1, if you plug in 0.1 there, well, 1 divided by 0.1 is 10. It's the same thing as the sine of 10. You can plug this in your calculator if you want. That's not the point. Then if you have sine of 0.01, you plug in 0.01 for x, it's the sine of 100. If you plug in sine of 0.001, it's the sine of 1000. And the funny thing is, the lower and lower you get, the closer and closer you get to 0, you're not getting any closer and closer to any number. Let me explain. If you think of like the sine graph normally goes up and down and up and down and up and down, always between positive 1 and negative 1. But what we're talking about here is like as the denominator gets smaller, your numerator is getting bigger, and like you're looking at sine of 10, sine of 100, sine of 1000. You never reach the end of sine. You never do. And so for that reason, what does the graph look like? It's crazy. The sine of 1 over x, if you plug this in your calculator, it gets crazier and crazier the closer you get to 0. It looks pretty normal at first, then it gets closer and closer and closer, and then in the middle it just like explodes, and then it gets further and further apart. It's a pretty cool function. I encourage you to graph it, and I encourage you to go into your calculators, your graphing calculators, and change the window. Change the window so you're getting closer and closer to 0, and you'll see that it just explodes. Like, you'll never get close enough. It's pretty fun. So the good news is, do you have to know any of these? No. Do not memorize these. You don't have to. I'm just showing you because it's fun. But what's important to remember is the words non-removable and removable discontinuity. Okay? So, oh yeah, and again, removable just means the limit exists. Non-removable means the limit does not exist. And with that, we're on to the final already the final topic of tonight. After we get through the final topic, we're just going to be doing example problems for the rest of the night, and that'll probably lead us into the end of the hour. But anyways, for the difference quotient, here's what it is. This looks confusing. Like, look at this formula. It's ridiculous. Well, what if I told you this formula is just an overcomplicated version of y2 minus y1 over x2 minus x1? That's all it is. Now let me prove it. I have a giant graph here, and let's, for this graph, look at the points 1 and 3. Let me make sure I line that up right. Close enough. So we have the points 1 and 3. In other words, what I want you to think is that this is our x is 1. I want you to think of x plus h as 3, which then means h, the distance from 1 to 3, h is 2. And why am I saying this? Because look at the formula. F of x plus h, f of x, h, blah, blah, blah. So these are the x values, this is the h value. Now this point right here, that y value is f of x, and the y value here is just f of x plus h. Because remember, y and f of x are just two words for the same thing. F of x is just a y value. Same with f of x plus h. So what I'm trying to get you to realize here is if I just replace x with x1, f of x with y1, x plus h with x2, and f of x plus h as y2, it's the same thing as a slope formula from Algebra 1. Now here's where it gets different. Basically what I'm doing, why I'm doing this, is I'm connecting a line like this. I'm finding the slope of a linear line, just like we would in Algebra 1. But the cool thing is that we're going to use this slope to do some pretty cool things later on. But any questions with anything I'm saying so far? Okay, if you do have any questions, don't be shy. I don't bite. I would bite in person, of course, but since this is virtual, I can't, so you're safe for now. Anyways, now we need to find the slope of the secant line, which, by the way, a secant line, don't even worry what a secant line is. It's just to find the slope of the line between x equals 2 and x equals 8 of the function f of x equals root 2x, which is below. So if I were to just quick draw a picture of this, here's x equals 2, here's x equals 8. If I were to draw a line connecting these two, it'd look like that. And really, I'm just doing x1, y1, x2, y2. But I don't want to do Algebra 1 notation. I actually want to show you in calculus notation, and there's a reason why. It's not just to be annoying. It'll make sense in about 10 minutes. But here's what I'm saying. Your x is 2, and your x plus h is your second number, which is 8. Can someone tell me what h is then?
H is 6.
Thank you, both of you. So yes, h has to be 6. Why? Because 2 plus 6 gets you to 8. So now I'm going to plug in the formula f of x plus h minus f of x over h. So for the numerator, remember, f of x just means plug it into the function. So plugging in 8 into the function, square root of 2 times 8, minus, plug in 2 to the function, square root of 2 times 2. Denominator is h, so that's 6. The numerator is going to simplify because 2 times 8 is 16. Square root of 16 is 4. Minus 2 times 2 is 4. Square root of 4 is 2. Divided by 6. And you plug that in a calculator, or you don't even need to, honestly. It's pretty easy. You get 1/3. In other words, the slope of this line, that slope is 1/3. Isn't that so cool? You found the slope of a line. Great job. Dan, why are you wasting my time with Algebra 1? I'll tell you exactly why I'm wasting your time with Algebra 1. Because basically, if you do this limit, and I think you're starting to see this, let me go back to the big example right here. You don't have to write this down if you don't want to, because this is going to get really cluttered really fast. But basically what I'm saying is we chose to find the slope of the line from 1 to 3. Why did I choose 1 to 3? That's actually pretty far off. Why don't I choose a closer number, like 2 for instance? See, if I do 2, that's an even better slope of the line. But why stop there? Because let me zoom in now. Let me zoom into 200% zoom, okay? And now let me choose this point right here, right there. Let's call that point 1.1 if you want. And that line in green is going to be even closer. Closer to what? I'm talking about the slope. I'm talking about the slope at x equals 1, which I'll draw in black. The slope at 1 is the black line. And let me zoom out now back to normal zoom. As you can see, the red was pretty far off from the black. The blue's getting closer. The green's like right there. But if you want the exact slope, then what does your h need to be? Your h needs to be 0. You need to add 0 essentially. Or maybe you can't add 0, so maybe you add 0.0001. But here's the thing, with limits in calculus, you actually can get down to exactly 0. So, what's the next example I have? X squared at x equals 2? Great. So here's what I'm saying. If I follow the formula, f of x plus h minus f of x, and by the way, I don't want you to write this down quite just yet. Just look for a second, okay? And they'll tell you what to write down. But if I have this, and I'm saying h equals 0, right? So let's plug in 0. So f of x plus 0 is just f of x minus f of x divided by h is 0. You'll see we get 0 over 0. Now some of you are thinking, oh darn, it didn't work. But those of you out there who say, hey, 0 over 0, we saw that a lot in week 1, lesson 1, and we figured out ways of dealing with 0 over 0. Which, does anyone remember what 0 over 0 is called? And remember, it's not undefined.
It's indeterminate, right?
Correct, indeterminate. And indeterminate means, it's ironic because it's called indeterminate, which sounds like English for cannot be determined. It's funny because it's the only example where you can actually determine it. It's ironic. But either way, we're actually going to solve this, and the way you solve it is using a limit. So now you can start writing. Let me just erase this first. Okay, now we can start writing. So if you do a limit for the same thing, remember with limits you don't plug in. That's direct substitution. As we just saw, direct substitution did not work. So the next thing we should try is probably factor and cancel. But how on earth is anyone, even the great Dan the tutor, gonna factor this? The secret is you don't factor this. This is impossible. You factor this, what I just underlined, x squared. In other words, plug in f of x equals x squared, but then what do you plug in for f of x plus h? I'm going to show you two things. One of them is right, one's wrong. It's either f of x plus h equals x squared plus h, or it's f of x plus h equals quantity x plus h squared. Cast your votes now. Don't say them out loud. Just think to yourself. And the correct answer is, oh, and by the way, let me just write the original right next to it. Okay, here's the original. The correct answer is this one. And this one is horribly wrong. So basically, when I say f of x plus h, what am I saying? I'm saying you take every x from your function and you replace it with x plus h like this. Let me show you a few quick examples, like rapid examples. This is not part of the problem, but I just want to show you this. If, for instance, f of x was the square root of x, well then I would say f of x plus h is square root of x plus h, because I replace the x with an x plus h. What if I have f of x equals x cubed minus 3x? Well then I would say f of x plus h, this is a tough one, I would say it equals the quantity x plus h cubed minus 3 times x plus h. Notice, every time you see an x, I am replacing it with an x plus h in parentheses. Does it have to be in parentheses? Most of the time, yes it does. Okay, so now back to our problem at hand. I want f of x plus h, which we actually just said what it was. we said it was x plus h quantity squared minus x squared over h. Okay, this is better. Still not great because, like, you can't cancel anything out right now. You're kind of stuck. Unless, of course, you do the right thing, and the right thing being FOIL out the x plus h. So what I'm saying is x plus h squared is really this. And if you FOIL it out correctly, and I'm going to skip the step where you combine the two xh terms, and you get this at the end, okay, if you FOIL correctly. Now I'm going to fill that in for my function. And with that, that leaves me with limit as h approaches 0, and yes, I have to write the limit each time. I know it's annoying, but that's good notation. Of x squared plus 2xh plus h squared, and then finally minus f of x, which was just x squared over h. I know this looks complex now, but hopefully you can see that your x squared terms cancel. And so what you're left with is the limit as h approaches 0 of 2xh plus h squared over h. Some of you may be stuck right now. I will tell you, this is where I factor. I factor out the h. In other words, the numerator has an h term in common, so if I factor it out, I'm left with 2x plus h. Now, there is an h in the denominator that cancels. By the way, you may be thinking, can I just cancel it out from here because they both have h in it? And the answer to that is technically yes, but I still want you to do it the long way, the hard way, because that's the correct way, technically, especially at the beginning. But once you get good at this, yes, I'll let you do that. And then finally, after you cancel, that's when usually I'm allowed to use direct substitution again. And there's why this makes sense, because if I plug in 0 for h, then I get 2x plus 0, which is just 2x. Now, many of you may be thinking, well, what the heck does this mean? What does 2x even mean? Is that my answer? And the answer is no. Because the question asked specifically for the slope at x equals 2. So now you're thinking, okay, then I plug in x equals 2. And sure, fair enough, you just plug in 2, okay, 2 times 2 is 4, and that's your answer. But if you don't understand the magnitude of what we just discovered, then you are missing out a huge, like the biggest revelation in all of calculus. And let me explain. Because what we just found, let me just show you x equals 2. Here's 2. Here's the point at 2. And what you just told me is that the slope, I'll draw it in red, the slope of my red line at 2, that slope is 4. And the truth is, you don't know just the slope at 2. You know the slope of x squared at literally any value of x if you just follow the formula 2x. Let me prove it. What does the slope look like at 0? Because to me, the slope looks flat, like at 0. Well, if you plug in 0 for 2x, 2 times 0 is 0, that confirms it. You know the slope at 0. Okay, fine, but what about a negative number? Like, for instance, what about the slope at negative 2, for instance? Like, here's negative 2 right here. Okay, fine. 2 times negative 2, negative 4. That slope is negative 4. You know the slope of the function x squared at any point you can possibly think of. And we did it because we know limits and because we're hopefully good enough at algebra and simplifying, and this is beyond algebra, this is like pre-calculus to be honest. But because we know how to simplify and we know how to do limits now, we combine those two to find slope. And the reason why slope is important and the reason why 2x is important is because you just found your first ever derivative. Give yourself a round of applause. You just found your first derivative. Very good job, everyone. And that's going to be the first of many. Now you may be thinking, that sucked, that took forever, and we're not even at the practice questions of today yet, and you would be correct about both of those things. The good news is, lesson 3 is all about shortcuts of everything we're doing today in lesson 2. So you're going to hate me at the end of next week when we make everything we just did obsolete. But until then, you have to do it. Every calculus class in the country does it this way first, including the AP exam. The AP exam, there will be questions that force you to do it this way. So, sorry, but we're going to do it the hard way first. Okay, now we're going to talk about the practice questions. Let's see if you remember what we said earlier about horizontal asymptotes. So remember, this question is asking about horizontal asymptotes, not limits, but we know the way you find it is by technically using a limit or that shortcut we talked about, which is saying, for instance, number 1, who's higher, degree of numerator or degree of the denominator. The answer is degree of denominator is higher. And the reason why is because x squared is higher than just 2x, because that's just x to the first power. So because of that, the answer is instantly y equals 0, and we're done number 1. By the way, you're going to probably learn another method. There is a longer, harder way of doing it, and I know I just said earlier I like the harder and the longer way, but not this time. I actually like this shortcut. It's a lot better. And then for number 2, we have a piecewise function. Piecewise functions are annoying because there are 2 potential answers. In other words, the behavior of the graph is doing something for the left side, which is x is less than 0, and it's doing something different for the right side, which is x is greater than or equal to 0. What do? I'll show you. You would first deal with the left side, which is like 1 over x, and for this one you would say, degree of denominator is higher. So we've got one horizontal asymptote at y equals 0. And just so you know, because this is a calculus class after all, and this is the limits section of the course, how you'd write this as a limit, you'd say limit as x approaches negative infinity, because that's what we're talking about, limits at infinity today. Limit as x approaches negative infinity, f of x equals 0. That's how you'd write that as a limit. But the question did not ask for limits, it asked for horizontal asymptotes. So technically I don't have to write this, but I'm just showing you anyway. Now for the right side, for the right, we're looking at the function 3x plus 4 over negative 5x plus 1. Hopefully you realize here the degrees are equal. And because the degrees are equal, it just means you look at coefficients. And so that means the answer is numerator 3, denominator negative 5, and there you go. Why 3 over negative 5? Because that's the leading terms. The x terms, they're the highest degrees, so you just divide the coefficients, 3 over negative 5, and you're done. So this one had 2 answers. The first answer was y equals 0. The second answer is y equals negative 3/5. Any questions on? Go ahead.
Yeah, sorry. Dan the tutor, I know that you said that we wouldn't have to put this in the limit, like the limit x, x to infinity equals 0 or that. But I see in the directions it says using limit notation. You have to find the horizontal asymptotes or something.
Well then perfect. Thank you for actually reading the instructions, unlike me. So yes, in that case, how would you write that for the right-hand limit? You would say limit as x approaches positive infinity, f of x equals 3 over negative 5. But also what you can do, it's perfectly fine to use this reason. You can use the degrees are equal reason. We're just saying with the instructions that you need to use the limit notation, I guess at some point in the problem. So I'm not going to lie, these questions are not exactly what you're going to see on the AP exam. I'm just showing you this so you get a pretty good idea of what we're talking about. You know what I mean? So with the actual AP exam, you're going to do one or the other. They're either going to ask for horizontal asymptotes or they're going to ask for limits. I'm showing you both because this is the first time you've ever seen either of this stuff. So let's continue then. Next question, you need to determine if the function is continuous over the point or the interval. Then you need to state 1, where it's discontinuous, and 2, the type of discontinuity, removable or non-removable. For number 3, it's a graph. We've got we're looking over the interval from negative infinity to positive infinity. We clearly see there's a hole in the graph right there at x equals 8. And we know holes in the graph, that is a discontinuity. So discontinuous. You can write discontinuous or you can write discontinuity. It's the same thing. At x equals 8. Okay, that's the first part. And by the way, the function's continuous everywhere else because there's no hole in the graph. There's no problems. And the other thing we want to say, is this removable or non-removable? Well, what did we say about holes in the graph? Is that removable or non-removable? Any guesses? It's going to be a removable one. And the reason why it's removable is because 1, the limit exists. How do I know the limit exists? Because holes in the graph, we say limits ignore the holes. So yes, the limit exists, which makes it removable. Okay, so now number 4. Number 4, you have to be careful because this is continuity at a point. If you look at the last one very closely, I said continuity over the interval, negative infinity to positive infinity. Continuity at a point is when you have to do the 3-step process, which I forget if we've done or not. I don't know. But here's what we're going to do. Step 1 is proving that the value exists. What does that mean? Well, you want to prove that this function exists at x equals 0. So that means plugging into 0 with the function, it's 0 squared, you get 0. Fantastic. Any number would have worked, but 0 is what we got. So since it exists, we didn't have to write DNE, we're good for step 1. And by the way, step 1 should basically always pass. 99% of the time. Step 2, which is the limit, this is where you could potentially run into trouble. So the limit as x approaches 0 of our function. Well, if you look closely, you can do direct substitution because there's no problem with plugging in 0 here. So 0 squared is 0, check mark, limit exists. Great. Step 3, does the value of the function equal the limit? Does 0 equal 0? And the answer is obviously yes, which means, yes, the function is continuous at x equals 0. And there's our answer to the question. So we do have to do all 3 steps. By the way, if let's say step 2 failed, you don't have to do step 3. Instantly you say not continuous. You're done. Any questions on that one? Okay, good. For the next one, number 5. This one's pretty long, but I'm going to show you some shortcuts that can make it go a lot smoother. You want to find where it's continuous over the interval from -1 to 6. So the good news is, since it's not a continuity at a point question, you don't have to do the 3-step process. The bad news is you've got a piecewise function. Now let's think for a second about what makes things not continuous. Obviously, if you've got like a domain error, for instance, a 0 in the denominator, if you have a negative square root, that's instantly going to make you not continuous. But because piecewise functions, here's what you do for piecewise functions. Here's the easiest way to do it. Set piecewise functions equal to each other at overlapping points. I'll give you a second to write that down. Set piecewise functions equal to each other at overlapping points. What does this mean? It basically means look at 2 functions that overlap. Like for instance, 1 over x and 3x. They overlap at x equals 0. So at x equals 0, I want to see if the 2 functions are equal to each other. So first I'm going to check 1 over x, which if I plug in 0 for that, that's a problem. You can't have 1 over 0. That's undefined, not indeterminate, which is not good. So basically what that means is it's definitely not continuous at 0. But let's check 3x anyway, just for the practice. If you check 3x plugging in 0, that's 0. Basically, since they don't equal each other, it's not continuous at 0. Well, specifically x equals 0. Let's say x equals 0. Now you're going to do the same thing. You're going to check x equals 5. When you check x equals 5, that is where 3x and x squared minus 10 overlap, as you can tell from the bounds of the piecewise function. So at x equals 5, you're going to say, first 3 times 5, because you're plugging in 5 for x, for 3x. That's going to be 15. No problems there. Then you're going to plug in 5 for x squared minus 10. That's 5 squared is 25, minus 10. You get 15. They equal each other. Check mark. So you are continuous at x equals 5. And so basically what you could raise your final answer, you can say continuous everywhere except x equals 0. This is fine for right now because this is really the 2 points I wanted to check. Any questions on number 5? Okay. Now for the last couple, we have 6, 7, and 8 left. The next one, we want to use the difference quotient to find where the secant line passes. So first thing we should do is we should find x is 0 x plus h is the 3 pi over 4, which then means our h is, you can think of it as 3 pi over 4 minus 0. H is also going to be 3 pi over 4. Very nice. Now remember, the difference quotient is not the limit part. This is actually the much easier part. It's like the y2 minus y1 over x2 minus x1, except we're going to use the better notation. We're going to write f of x plus h minus f of x over h. And the good news is, from here, it's basically the same thing. Let me explain. For the first one, you're just going to plug in 3 pi over 4 into 2 sine x. In other words, 2 times the sine of 3 pi over 4 minus plugging in 0 into the function. So 2 times sine of 0. And then divided by h, which is 3 pi over 4. Okay, now can someone tell me what the sine of 3 pi over 4 is? I'll give you a hint. It's in quadrant 2.
Is it root 2 over 2?
It is root 2 over 2 and positive because sine is positive there. Very good. So that means 2 times root 2 over 2. And then who knows the sine of 0? Yeah, that's just 0.
0.
Thank you.
Yeah.
So then divided by 3 pi over 4. And now it's just a matter of simplifying this. So 2 times root 2 over 2. We can say these 2's cancel. So in the numerator, you've got root 2 minus, well, really 0, so I don't even have to write minus anything. And then it's a complex fraction divided by 3 pi over 4. I hate complex fractions. I'm going to deal with this by multiplying by the reciprocal, which looks like this. And so your final answer is a beautiful 4 root 2 over 3 pi. Yeah, great one, right? Now this number is actually pretty close to 1, in case you're curious. But anyways, let's continue. That's it for number 6. Now let's look at number 7. Number 7 is basically the exact same thing, except we've got a new function. So f of x plus h, I just want to plug in 2 into the function. So negative 8 times 2 squared plus 7, and then minus, when I plug in 1, make sure it's the quantity. Put that in parentheses. Negative 8 times 1 squared, which is still just negative 8, plus 7. And then remember, all divided by h. Well, if x was 1 and x plus h is 2, well, then h must be 1. So 1 in the denominator. And so now all we need to do is start simplifying this. So my numerator, negative 8 times 2 squared is 4. That's negative 32 plus 7. And then minus negative 8 plus 7 is negative 1. Minus negative 1 is plus 1. And then divided by 1. Okay, if you simplify this, you'll get a final answer of negative 24. And there's our answer for that one. Any questions? Okay, good. And now the very last question. This one is the hardest one of the bunch. It is use the limit definition of derivative to find the slope of the function at the given point. This is with the big daddy, where limit is h approaches 0 of f of x plus h minus f of x over h. And this is where you have to do that f of x plus h thing we were doing earlier. Let me explain. F of x is just the function negative x squared plus 1. We're going to plug that in right there in a minute. But first we have to find f of x plus h. Go ahead, take a few seconds, don't say it out loud. Try to tell me f of x plus h on your own. If you get stuck, I'll give you the answer in 15 seconds. If you're watching the recording, try it on your own. Okay, time's up. I'm not sure if that was 15 seconds or not. Frankly, doesn't matter. The answer is negative parenthesis x plus h close parenthesis squared plus 1. Now the harder part is we now need to simplify this. So order of operations, PEMDAS, tells me that exponent comes before the negative sign out in front. So in other words, I got to square this. You got to FOIL it just like we did before. It's going to be very similar actually to what we had earlier. It's going to be negative quantity x squared plus 2xh plus h squared. Again, if you FOIL, that's what you get. Close parenthesis, cap it off with a plus 1. Now I'm going to FOIL the negative sign to each of these terms. We'll get negative x squared minus 2xh minus h squared, but the plus 1's still plus 1 because it wasn't in the parentheses. And there we go. There's f of x plus h. As you can tell, this one's much harder than the other one we looked at, but the answer is just as simple, if you'd call it simple. Next step is limit as h approaches 0. We now plug in f of x plus h. We just said it, negative x squared minus 2xh minus h squared plus 1. And then minus the quantity. Be careful here. Minus the quantity. The original f of x was negative x squared plus 1, close parenthesis, all divided by h. How on earth is this going to work out? Well, I gave you a whole page, so I hope it does. So the next thing we should do is we should distribute the negative sign here. We're basically going to get the exact same thing, except now it's plus x squared and minus 1 all over h. I'll give you a second to catch up with me. I know I write fast. And as you're writing, I will make the astute observation that it looks like these x squareds will cancel, negative x squared and positive x squared. It also looks like the plus 1 and the minus 1 will cancel, which means all I'm left with is negative 2xh minus h squared over h. Can you cancel out the h's at this step? Technically, yes. I will not. I will factor out an h instead, which is technically the same thing. H times the quantity, what's left? Negative 2x minus h all over h. H's cancel, and now I can plug in 0 for h. Your answer will be just negative 2x minus 0, which is negative 2x. However, I shouldn't circle that answer because the question's not asking me to find the derivative, because this is what this is, the derivative. The question's asking to plug in x equals 2. So when I plug in 2 here, negative 2 times 2, I get negative 4. In other words, that's the slope of my function at the point x equals 2. Any questions there? Okay, then with that, that is the end of the lesson. I will now be uploading this recording to YouTube and sending the link to everyone, and I'll also be sending out the problem sets, which hopefully I didn't make a mistake like I did last time. I won't have to make corrections. We'll find out together pretty quickly. So, thank you all for attending. I hope you have a great rest of your night, and bye-bye.